Hi everyone, this is Empavan from Data Science Branch, IRE College. Now I am here to explain you one topic called scalable, secure, and highly available distributed file access. Today in our session, we are going to learn how the file access is going to happen. So without any delay, we will move on to our next slides. This is the introduction part of our topic. For the users of a distributed system to collaborate efficiently, the ability to share data easily is vital. Over the last decade, distributed file systems based on the Unix model has been the subject of growing attention. Andrew and Coda are distributed Unix systems that embody many of the recent advances in solving the problem of data sharing in large, physically dispersed workstation environments. Intended for the same computing environment as Andrew, Coda retains Andrew scalability and security characteristics while providing much higher availability. So the main thing of our today topic is to how the files are sharing and how the large data is going to share in without any problem or any issue. So for this case, we are using Andrew and Coda Unix systems. These are the two Unix systems that we are using for the transmission of data in large cases. So how these things are worked out and how they are coming into progress, we need to see those things in our session. Okay, the Andrew architecture. The Andrew computing paradigm is a synthesis of the best features of personal computing and time sharing. It combines the flexible and visually rich user interface available in personal computing in the case of information exchange, physically of time sharing. So here in the figure 1, we are going to see that a high level view of the Andrew architecture. The structure labeled V's is a collection of trusted file servers and untrusted networks. The nodes labeled W are private or public workstations or time sharing systems. Software in each such node makes the shared files in Wise appears as an internal part of that node's file system. This is how the high level view of an Andrews architecture goes on. So just look into that. That Wise is the main thing, main server, and the remaining W's are the temporary or private workstations. In this way, the architecture goes on for the Andrews. Then next we will move on. So this is in the figure 2, file system view at a workstation. How the shared file in Wise appear to a user. The subtree under the directory labeled AFS is identical at all workstations. The other directories are local to each workstation. Symbolic links can be used to make to, to, co- to make local directories correspond to directories in Wise. So this is how the user can able to see those local files when they are sharing and when they are when they are in under process in this figure 2. So we will move on next to learn about this more. The large Amoeba-like structure in the middle called Visa is the information sharing backbone of the system. Although represented as a single entity, it actually consists of a collection of dedicated file servers and a complex local area network. Data sharing in Andrew is supported by a distributed file system that appears as a single large subtree of the local file system on each workstation. The only files outside the shared subtree are temporary files. and files essential for workstation initialization. A process called Venus running on each workstation medicates shared file access. Venus finds files in Wise, catches them locally, and perform emulation of Unix file system semantics. Both Wise and Venus are invisible to workstation processes, which only see a Unix file system. Scalability in Andrews. A scalable distributed system is one that can easily cope with the addition of users and sites, its growth involving minimal expenses, performance degradation, and administrative complexity. AFS1. AFS1 was a prototype with the primary functions of validating the Andrew file system architecture and providing rapid feedback on key design decisions. Each server contained a local file system mirroring the structure of a shared file system. The Wise file status information, such as access list, was stored in shadow directories. If a file was not on a server, the search for its name would end to would end in a subdirectories that identified the server containing that file. Design principles from Andrew and Coda. These are the things that design principles. Workstation workstations have the cycles to burn, catchy whenever possible, exploit file usage properties, minimize system-wide knowledge and change, trust the fewest possible entities, bench if possible. Just go through these things for the design principles from Android Coda. Once I learn about these things in detail, then you will easily understand what the uses of these words. Okay, AFS2. The design of AFS2 was based on our experience with AFS1 as well as on extensive performance analysis. We attended the strategy of workstations catching entry files from a collection of dedicated autonomous servers. A fundamental change in AFS2 was the manner in which cache coherence was maintained. Instead of checking with a server on each open, Venus now assumed that cache entries were allowed unless otherwise notified. AFS2 used a single process to service all clients of a server, thus reducing the context switching and paging overheads observed in AFS1. A non-primitive, lightweight process mechanism supported concurrency and provided a convenient programming abstraction on servers and clients. This in the figure 3 AFS2, Venus Sun's NFS performance under load on identical client server and network hardware. A load unit consists of one client workstation running an instance of the Andrew benchmark. Full details of the benchmark and experimental configuration can be found in Howard, from which this graph is adopted. As the graph clearly indicates, the performance of AFS2, even with a cold cache, degrades much more slowly than that of NFS. Here you can observe the cold cache and warm cache through the diagrams of O and delta and a small square NFS. See how those things are going on. So in this way you can understand what the things are raising and what the things are in the middle and what the things are in down and how they are started and how they are ended. Throughout these things can be observed in this diagram. Security in Andrews. The most important thing, one of the important thing in our file transfer is security. It is one of the main aspects. So Andrew provides mechanism to enforce security, but we have taken care to ensure that these mechanisms does not inhibit legitimate use of the system. Andrew predicates security on the integrity of the much smaller number of voice servers. No user software is ever run on servers. Workstations may be owned privately or located in public areas. Andrew assumes that the hardware and software on workstations may be modified in arbitrary ways. This session summarizes the main aspects of security in Andrews, pointing out the changes that occurred in the system evolved. These changes have been small compared to the changes for scalability. More details on security in Andrew can be found in an earlier work. So in the figure 4, major components and relationships involved in authentication in Andrew, modifications such as password changes and additions of new users are made to the master authentication server, which distributes these changes to the slaves. When a user logs in, a client can obtain authorization tokens on the user's behalf from any slave authorization server. The client uses these tokens as needed to establish secure connections to file servers. See, this is how all the things are connected to the client. The file servers, slave authorization server, and all those things, new passwords, changing, everything will be connected to the client. This is the most one of the important thing. Protection domain, authorization, file system protection, resource uses. These are the main aspects we need to consider in case of security Andrews. According to the performance of these functions, the security of the Andrew depends. Means in when we are considering the security of when we are considering the security of transferring files, we need to consider about these four important things in Andrews. Those are protection domain, authorization, file system protection, resource usage. And next we will move on to next slides. Highly availability in Coda. When network partitions were occurs, writes, Coda allows data to be updated in each partition but detects and confines conflicting updates as soon as possible after their occurrence. It also provides mechanisms to help others recover from such conflicts. A related goal of Coda is to gratefully integrate the use of portable computers. At present, users manually copy relevant films files from Visa, use the mission while isolated from the network, and manually copy updated files back to Wise upon reconnection. Coda provides failure resiliency through two distinct mechanisms. It uses server replication or the storing of copies of files at multiple servers to provide a highly available shared storage repository. Figure 5, servicing a cache miss in Coda, the events that follow from a cache miss at the client, both data and status are fetched from server 1, which is the preferred server PS. Only status is fetched from server 2 and server 3. The calls to all three servers occur in parallel. So see how the client is connected to the servers in this way. The mechanism of building distributed file systems, mount points, client hatching, hints, bulk data transfer, encryption, and replication. These are the things we need to consider when the mechanism for building distributed file systems. Conclusion. Throughout the evolution of the Andrew and Coda file systems, the underlying model of computation has remained unchanged. The security of the system is not contingent upon the integrity of the workstations or of the network. The problems of scalability, security, and availability will continue to be important as distributed file system grows in size. In conclusion, we have made such progress in the design and implementation of distributed file systems over the last decade. Andrew and Coda embed many of the key advances made during this period. Thank you for giving me this wonderful opportunity to share you my knowledge. Have a great day. Thank you.